So this is a continuation of Chapter 8 notes. What I'm going to talk about is how do we actually draw some of these more complicated molecules, ions, whatever you want to call them. So there is a multiple steps that you're going to take place, and the steps will make a lot more sense once we do a couple examples. But first thing you're going to do is count all of the valence electrons that are in the molecule itself. You're going to put the first atom as the central atom, and this we will add to this when we talk about something called formal charge, where you actually have to determine what the central atom is, but I will kind of point to that a little bit later in the notes. Make single bonds around the central atom, complete the octet around each atom, and then any extra electrons you might have is going to go on the central atom as lone pairs. So the biggest question mark has always been, well, if you have something like nitrogen, and I have essentially 5 valence electrons around nitrogen, well, does that mean nitrogen only makes 3 bonds? So what we're going to learn is using this method is that you can essentially go beyond the octet and also explain some other molecules that don't fit into just what the valence electrons are for that central atom. So we're going to go over some polyatomic ions. And the first one we're going to talk about is phosphate, okay? So PO4 3-. So when I am looking at an ion or a molecule, what I'm trying to do is add up all of the valence electrons contributed by everybody. So phosphorus has 5 valence electrons, oxygen has 6, and you have 4 of those. And then I have the -3. So if I have a -3, that means I have 3 electrons being donated from somebody. So I have a total of 32 electrons. And I'm going to divide this number by 2 so I could do it according to lines. So if I have the first atom here as phosphorus, okay, I'm going to put single bonds with the 4 oxygens. So I'm going to put a single bond to each one of the oxygens. And then I see that phosphorus has a complete octet. So now I'm just going to put valence electrons, lone pairs around each oxygen to complete their octet. And so now if I count up, I have 4 plus 4 plus 4 plus 4. I have 16 electrons, so or 16 lines. So I now have a complete molecule. So that is an okay way of drawing it. The only additional thing that we will be doing is putting brackets around anything that has a charge and to say what the charge is, because a phosphorus and 4 oxygens do not contribute to a total of 32 electrons. This structure would not work otherwise. So you need 3 electrons being donated. Again, phosphorus starts off with 5 valence electrons. So that means it should only make 3 bonds. But this molecule, this ion, does exist. So what I want you to think about with these electrons, okay, is that you've been invited to a party, and everybody's supposed to bring something to the party. So say it's cupcakes, chips, soda, whatever it happens to be. When you go to that party, everybody shares your cupcakes. Everybody shares with what you brought. So think of it as the electrons. So these 5 electrons don't just belong to phosphorus. You could spread them out through the whole molecule. So the valence electrons try to do that. So see if you can draw PO3 3-. See if you could pause the video, see if you could draw it. So this would be how you draw PO3 3-. Again, phosphorus, you connect it to the 3 oxygens. You complete the octets with the lone pairs, but phosphorus does not have 4 lines around it, so you need to put a lone pair there. And then you count up all of the lines and you have the correct number of lines, and you put a -3 on the outside. So we do have other molecules that I'd like to talk about. So let's do carbonate, CO3 2-. So let's count up the valence electrons first and see where we go from there. So carbon has 4 valence electrons, oxygen of course has 6, and then I have 2 because it is a -2. So I got a total of 24 electrons, divided by 2 is 12 lines. So in my structure, I'm going to have 12 lines. I'm going to put carbon in the middle, then I'm going to put my 3 oxygens on either side. Then I put my lone pairs around the oxygens, okay? And then I go, okay, well, who doesn't have 4 lines around it? Who has not completed the octet? Well, that would be carbon, okay? So now if I count up my lines, I have 4 here, 4 here, 4 here, plus another one, that's 13 lines. So I have too many lines. I can only have 12 lines in my structure, so this cannot be the structure, okay? So if that's the case, I have to consider doing a double bond. Okay, so if single bonds don't work, then you need to go to double bonds. If double bonds don't work, have 2 double bonds. If that doesn't work, try a triple bond. Now realize the oxygen that has the double bond is going to have 2 lone pairs. Okay, that's going to give you 12 lines in the structure. Now, could I have drawn the double bond over here on the left? Sure. Could I have drawn the double bond on the bottom portion, bottom oxygen? Sure, okay. So what I have here is essentially a discussion of something called resonance, okay. Now when we discussed it before, okay, we kind of said, oh, well, it's because you could have 3 different structures, okay, when we taught it to you first year. So instead of drawing those 3 structures, what we told you to do is to draw one of them. I need to put brackets around it and put a minus on the outside, but then just draw a double-headed arrow underneath the structure. And then we say we could have that double bond in all 3 locations. That's really what it is. So I want you to write down on your notes here, okay? Resonance, okay? Resonance is the electron density is distributed across the whole structure. That's really what resonance means. So if I go back to my drawing here, okay, really what I have is not a single bond between the carbons and oxygens, but what I have is what I call a bond and a third. So what you will sometimes see books do is they do like a dotted line to say that essentially that double bond is throughout the whole structure. So if I divide it by 3, it's essentially a third of a bond, a third of a bond, a third of a bond. So part of the time it's here, part of the time it's here, part of the time it's here is where the electron is located. And how we know this is by what we call the distance between the carbon and the oxygens. We can now measure that distance. So a single bond looks a particular way, a double bond looks different. And so when they look at a molecule like this, they see that it doesn't have a structure that is a single bond, nor is it a double bond. So therefore, it's got to be some kind of resonance structure. All right, so why don't you, to kind of add to this just a little bit, if I have PF3 versus PF5, do realize that you can go what we call beyond the octet. Okay, so phosphorus does typically make 3 bonds, you know, and it has a lone pair. But PF5 actually exists. Okay, that molecule is actually a known molecule. So what's going on here? Okay, I have phosphorus with 5 valence electrons. How am I getting like an expanded octet? So anytime I give you something to draw, please note that I'm not going to try to fool you and have you draw something that doesn't exist. But realize that phosphorus, sulfur, and xenon can go beyond the octet. So that means around themselves, they could have more than 4 bonds. Okay, so don't overthink it. So see if you could draw these 3, and then I will come back on and show you the answer. So IF2 minus, again, you only have 2 bonds to make with fluorine, and so you have the extra electrons are going to go around that central atom. So you have 3 lone pairs on iodine in the middle, is how that structure can work, and you put a negative on the outside. ClF4, again, you could make 4 bonds with fluorine, but again, you have an extra set of electrons that you could put as a lone pair. And chlorine can't exceed the octet. Again, just draw it, and any extra lone pairs go on that central atom. And then finally, this last one, ASO3 minus. I have to put a double bond somewhere. Otherwise, I have way too many lines if I put a lone pair on that central atom. So therefore, I put a double bond here. Again, like I showed you in the previous example, I don't have to draw all structures. I just have to put a double-headed arrow underneath and to show that it has resonance. And again, put brackets on the outside and a negative sign.